the geophysics department with Tom Chafee. And a fun fact about Mateo is that he's never broken a bone. So 7 minutes are yours, Mateo. Thanks.
So, hi everybody, my name is Mateo Chavez, and I'm a second-year physics major here at Foothill College. Thanks to SLI here at Foothill, as well as the Stanford Geophysics Department, I've had the privilege this summer of developing a method for preventing rust while heating rare extraterrestrial materials to understand their magnetic properties. And before I get into what I've done over the past 9 weeks, I thought I would just give some quick definitions of some terms that may come up. So firstly being lunar paleomagnetism. This is the study of the moon's ancient magnetic field, which is preserved in rocks and minerals. Next being a dynamo. So a dynamo refers to the process by which the liquid metal core of a planet generates a magnetic field. On the moon, this occurred billions of years ago. And the moving metal created electric currents, which then produced a magnetic field. And over time, this magnetic field got locked into the rocks of the moon's surface. The project that we're working on this summer is mainly done to move forward the field of lunar paleomagnetism. And on the right, we see a timeline of the lunar dynamo, and all of the points are individual experiments on moon rocks of different ages, showing the strength of the lunar dynamo when that rock formed. I'm sure you're able to see a pretty clear gap at about the 1.5 billion mark to present. You can see a lot of these points also have big error bars on the vertical axis. This means that we're uncertain of the magnetization strength as the methods we used were imprecise. That's because it's a lot harder to experiment with moon rocks because they're very easy to rust in the Earth's atmosphere. So for ordinary Earth samples, heating experiments are sort of the gold standard. We have to heat the rocks up to 700 degrees Celsius to fully demagnetize them. Being able to apply that technique to lunar samples without oxidizing them, which destroys the original magnetic minerals, represents one giant leap forward in our abilities to accurately and precisely assess paleomagnetic data from the moon. So my mentor's research interests are really centered in a lot of different aspects regarding the moon, but specifically over the past 9 weeks, we chose to focus on trying to develop a method to heat lunar materials while also preventing oxidation. We're trying to prevent this oxidation because when these lunar samples become oxidized, the magnetic properties become altered. This can either erase the original magnetic signals or introduce new misleading ones. My goals for the summer are really to help me develop as a research scientist and gain lab experience. So here we have a range of magnetic instruments that we use to gather data this summer. First being the 2G magnetometer. So with the 2G, we utilize what is known as a SQUID, which stands for Superconducting Quantum Interference Device. And this allows us to detect and analyze the very weak magnetic signals preserved in these ancient lunar samples. The next instrument we used was the controlled atmosphere oven. This allows us to thermally demagnetize the lunar samples while also replicating the lunar environment to prevent unwanted oxidation. And the last instrument we used this summer was the Kappa bridge. So this is shown on the top right of the slide. And this instrument tells us how much of a sample becomes magnetized when exposed to a magnetic field, so we can see if oxidation has occurred and change the magnetic properties of the sample. The first step this summer for me was to familiarize myself with the field. So this meant reading a lot of different scientific papers as well as textbooks. And next was setting up of all the instruments that we used as well as calibrating them. We did this with the iron standards, which were 99.8% pure iron. So we would heat these samples and then compare its appearance to the susceptibility to determine the amount of oxidation that occurred. And as a control, we first did this in the Earth's atmosphere. And next we needed to make sure we had no leaks in our atmosphere controlled oven. So we very extensively leak tested it with a spray bottle. If it bubbled, we had a leak we needed to fix. No bubbling meant it was not leaking. And once the system worked, we repeated the control experiment, but now with an oxygen content matching the moon's atmosphere to show that there's less alteration and to prove our system actually worked. So here we have a picture on the left. This is the first iron standard that we tested. We heated the sample up to 500 Celsius in the Earth's atmosphere. And you can see how the metallic sample turned really black and it was oxidized in the after picture. We then repeated this experiment with an identical iron sample and also heated it up to 500 Celsius, but this time in our controlled atmosphere oven. And you can really see on the right, there's significantly less oxidation. So we measured only a 2% difference in magnetic susceptibility. And this shows that the sample only got partially oxidized on the outer layer. And ideally, we want this before and after picture to look exactly the same with no oxidation or rust at all. We think possible reasons that our sample oxidized despite setting the correct oxygen levels might be that there may be some impurities in the gas we used, or the model numbers for the atmospheric composition need to be corrected to our experimental setup, which will take more calibration later in the future. And that takes us to the next steps of this project. So the first being doing more calibration of the instruments in order to perfect our method and completely prevent oxidation. And in the future, developing a piece of software that could automate the increases in temperature and the changes in oxygen fugacity, which would ensure more accurate data and less chance of accidental oxidation during the finely tuned lab protocol. With this, be able to run full thermal demagnetization experiments on these lunar samples and gather reliable data. And also just to mention, these pictures on the right are the actual samples that will be used eventually when the method is perfected. And they were all collected from the Apollo 16 mission by astronauts. So over the span of the past 9 weeks, I've learned so much. I was able to gain a lot of valuable research as well as data analysis skills. As for various challenges and setbacks, we lost a couple of days of progress when the oven actually broke on us when we were running gas through it. So the seal just popped off, and you can see this in the right photo, the silicone seal. So we had to reapply that, and that took a couple of days. But this internship really helped me recognize how much I enjoy research and being in a lab, and also really helped cement the ideas I learned in my physics classes. And this experience also further motivated me to pursue a PhD. And as for the acknowledgements, I really want to start by saying a big thank you to Sophia for connecting and providing me with this internship opportunity. And in the time I've known her while I've been here at Foothill, she's always been very kind to me, and she's constantly pushing me to do better. She's always recommending a lot of internship opportunities, a lot of research opportunities to me, and I really appreciate that. Next, I want to thank Professor Sonia Tiku, as well as all the other interns and grad students for really making me feel welcome in the geophysics department this summer. It truly was an amazing experience. And lastly, I want to thank Tom. Tom put in countless hours with me. He answered every question I had, and I asked a lot of questions. And by the end of the internship, I really felt as though I had gained both a mentor and a friend. And this is just a photo of Tom and I in the lab that one of the other grad students took. And I thought it was just an appropriate photo to include. Yeah, that's my presentation.
Great, thank you, Mateo. I love your pictures with your thumbs up everywhere. That's awesome. It looks like you had a great